And so when we last left off, we got to the meaning of life. And what we said was that the most important concept and the reason why matter does what it does, why reactions occur, everything comes down to one simple phrase. Size does matter! And the smaller you are, the more attractive you are. Now, we're going to refer to this idea as atomic radius, because here's what we find. When we're looking at our periodic table, understanding the size of an atom is going to tell us a lot about how it is going to behave. So, in order to understand atomic radii and sizes of atoms, what we need to do is we need to revisit that idea of effective nuclear charge. And so in order to help me, what I'm going to tell you right now is that when we talk about atomic radius, the trend, in other words, the general rule of thumb, is that as we go down the periodic table, so in other words, as I travel down a group, right, so whoop, as we go down, we're going to say that the atoms increase in size. So size increases. So everything gets bigger as we go down. Now, here's where it gets a little bit contrarian. As we go across, so in other words, as I go across the periodic table, so literally whoop, from left to right, we find that elements will decrease in size. So get smaller. Now, my suggestion is instead of worrying about up, down, left, right, is you remember and focus on the two corners. And here's what I mean by corners. So over here, we have helium. So let's see what we know about helium. He's all the way up the top, and he's all the way on the right. This is going to be my smallest atom. Okay, this is my smallest atom way over here at the top. And then down over here in the lower left-hand corner, we have francium. So it's all the way at the bottom, it's all the way on the left, and so this is going to be my largest atom. And so I say focus on the corners because if you can do that, then it becomes very easy to say as I go down, I get bigger. As I go across, I get smaller. Okay, simple as that. Now, that's the booby prize. Anyone can kind of memorize that and kind of relate that, but the real question is, well, why is that the case? Why, as we go down the periodic table, are my elements getting bigger? And in order to help us with that, what I'm going to do is I'm going to write very quickly a couple of electron configurations, just so that we can refresh our memory of how it all kind of fits together. And so what I'm going to do is I'm going to focus on lithium and sodium. And so lithium would be 1s2, 2s1. And sodium is going to come in at 1s2, 2s2, 2p6, 3s1. And so if I ask the question, well, okay, so given this information, how many valence electrons does lithium and how many valence electrons does sodium have? You would probably say that they both have one valence electron. Well, why is that? Well, because I remember that my valence electrons are the electrons that are in the highest energy level. And so in both the case of lithium and sodium, the highest energy level is going to be, in the case of lithium, the second. In the case of sodium, it's the third. And in each of those, it only had one electron in that S shape. So both of these have one valence electron. Okay, great. How does any of this relate back to size? And so here's the question. What was energy level synonymous with? And if you recall, energy level was synonymous with distance from nucleus. And why do I say it that way? Well, because as I increase in energy level, I'm literally getting further and further away from my nucleus. So what we're going to find is that as I look at any of the elements on the periodic table, as I travel downward, as I compare, let's say, lithium to sodium to potassium, or even something like, let's say I did copper to silver to gold, right? As I go down each successive row, I increase in energy level, and therefore when I increase in energy level, I get further away, right? The electrons repel me and push me away. So when we go down the periodic table, when we go down a column, we find that the size of the atom increases. That I'm good with. But here's the one that always threw me for a loop. Why, when I'm going across, is my atom getting smaller? So what's going on, right? Aren't I adding more electrons as I go from left to right, just like I was doing before? And the answer is that as I go across, I do not increase in energy level, but I increase in effective nuclear charge. Whoa, what on earth does any of that mean? Well, let's take a look. And for this, let's compare something like my aluminum to silicon and phosphorus, right? And so for these, I'm going to do what we did a moment ago. Let's just go ahead and write down roughly what the electron configurations are going to look like. And I'm going to do the condensed version just so that for space we can kind of see it. And so when I condense these, let's say we're going to have neon in brackets. So this over here, we're going to have, for aluminum, it's going to be neon in brackets, right? And then we're going to have 3s2, 3p1. So it's going to be 3s2, 3p1. For our silicon, it's going to be the same thing. We're going to start off with neon in brackets. And we're now going to have 3s2, 3p2. And finally, for my third one for phosphorus, we're going to have, as we've already seen, my neon in brackets. And now this is going to be 3s2, 3p2. Okay, good. So far, so good. So now, why is my phosphorus smaller than my aluminum? Well, if I asked you, what is the highest energy level in aluminum, what would you say? And you'd look at it and you'd say, well, it's the third energy level. Look, I have some elements in the, some electrons in the S, and I have some electrons in the P. Well, what's the highest energy level in silicon? And just like before, I would look at this and I would say, well, you know, in silicon, we're going to see that I have the third energy level and the third energy level. I have 2 in the S and 2 in the P. And what's the highest energy level in neon? And you're going to tell me what's the third energy level. But now I have 2 in the S, and this should actually be 3 in the P, right? And so the highest energy level in all 3 of these was the third. The third energy level was the highest energy level, which means that all of the electrons were roughly the same distance from the nucleus. They were all in the third energy level, however far that is. But what happened in my nucleus as I moved from aluminum to silicon to phosphorus? And the answer is that when I look at this, as I moved across these 3, what I find is that I increased the number of protons. So aluminum had 13 protons, silicon had 14, and phosphorus had 15. And so if I stop and I think about this, I can sit there and I can say, look, so sake of argument, I started off with, in essence, aluminum having electrons in this third energy level. Now, again, I'm doing this very roughly, but you'll understand, right? And in this third energy level, again, here was his outermost electron, just one of the outermost, right? And so it was this distance away because it was the third energy level, et cetera, et cetera. Now, when I went from aluminum to silicon, what I did was that I added another proton. Boop! But the electron didn't get placed further away. The electron got placed at a similar distance. So let me get this straight. I cranked up the attractive power of the nucleus, and the electrons were a similar distance away. As the nucleus becomes more and more positive, it's actually going to tug and it's going to pull that valence shell closer and closer together. And the reason why it's doing that is because as I go across the periodic table, my effective nuclear charge increases. And the way that we can solve for it is we say that the effective nuclear charge, the Zeph, is equal to the number of protons minus the number of core, and this is important, core electrons. Now, what was a core electron? Well, in a nutshell, it was any of the electrons that weren't valence electrons. It were any of the electrons that were inside, right, or at a lower energy level than wherever the valence electrons were. So in the case of something like aluminum, I'm going to see that aluminum, again, would be 3s2, 3p1. And it had neon, it had neon in brackets. So let's see what I'm writing here. Well, what I'm saying is that neon had a total of 10 electrons, and all those electrons were at a lower energy level than the ones in the 3s2 and the ones in the 3p1. So if I wanted the effective nuclear charge of aluminum, I would sit there and I would say it has 13 protons minus these 10 electrons from that would be the core electrons, and so the effective nuclear charge of aluminum is going to be +3. Okay, well, that's nice. Well, who cares? Well, now let's compare it to something like silicon. And when I look at silicon, again, what I'm going to do is now in this case, I'm not going to have, right, 3 valence electrons. With silicon, we had 4 valence electrons. And so now what's going to happen? Well, silicon increased the number of protons. So silicon now has 14 protons, but it has the same number of core electrons as aluminum did. So when I do my subtraction and I say 14 minus 10, now the effective nuclear charge of silicon comes in at +4. Now, what that means right now, I don't know. I may not be able to say a whole lot about that. But what I can say with certainty is that silicon is better at attracting electrons than the aluminum. Why? Because for whatever reason, the protons in the nucleus of silicon are able to overcome the shielding effect of the core electrons. How about the same 10 electrons that aluminum had for its core and the same 10 electrons that silicon has for its core? When you compare those 10 to 13 versus 14 protons, the more protons you have, the more attractive you become. And as atoms decrease in size, then just like playing with magnets, if you have a positive charge over here and your negative charge is this far away, there's not a lot of an attractive force. But if you have your positive charge over here and right next to it you have your negative charge, sink, then those charges are going to do a bang-up job of attracting one another. And so when we talk about periodic trends and we talk about this idea of efficacy or ability to bond or take and steal electrons at all times, the golden rule is size does matter. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.